This video is just meant to give you a quick overview of all the different style cards that I've made. And if you have more interest, you can go to Github. I'll give you the link below, and you can download all the pertinent data for any particular card or all of the cards. I hope you enjoy them. Download them, use them, improve on them. Let's all have fun. Okay? With this combination of cards, I have a total out of the box of 160 inputs, digital inputs. I have 80 digital outputs, 160 servo motors that I can control from I²C, and 40 Tortoise motors that I can control, 20 of which have local matrix control on them. So again, enjoy them. I hope you like them. Thank you. Let me start off again by looking at the block detector block. We just went through this in a little bit of detail a minute ago, but I thought I'd just show you its size in comparison to everything else. So if I lay it down here, it's showing up about 2 inches by about 1.5 inches. So it's rather small. One thing that I didn't do that I wish I had done on this board is I didn't put an area for a mounting screw. I should have left an area out here where you could have at least stuck one screw through it. There are people that are complaining that sometimes the double-sided tape doesn't hold forever, and then it's a mess to clean up. But a lesson learned, so I'll learn that and move on for the next one. This is a 16 input card that I built. Okay, and along this edge, this is your 12 volts input, and this is your 18 volts AC input. The AC input goes to the bridge rectifier to become DC. It's filtered, smooth out the little ripple in it somewhat. The output from this arrangement is fed to the 12 volt regulator, and the output from the 12 volt regulator is fed to the 5 volt regulator. And these two voltages then are used on the board. The 5 volts is used for the control logic, the 12 volts is used for the field devices. The next terminal is the RS485. This is where you connect your computer wires, okay, using the RS485 USB adapter. And that works with the Max 485 chip. And that's responsible for getting the ones and zeros, the on and off voltages into the card. And of course, then we have the Arduino Nano, which is loaded with the computer code that translates what's coming in from JMRI to the hardware output pins, and then also translates what's on the hardware input pins in and sends it out to the JMRI. This side, of course, there's 2 banks of 8 inputs each, and the small terminal strip down here is a convenient field ground. So what you would do is you take a wire from here out to your switch, through your switch, and back to any of the desired inputs. To help protect the board, I've installed a diode on each of the inputs. So if you get reverse polarity, nothing gets damaged. And also, I have the current limiting resistors built into the board, so that you don't have to have any external devices other than the switch to tie into here. To go along with all this, well, let me finish the board first. These are the opto-isolator chips, and these chips, one side is 5 volts, and then there's an infrared signal controlling an internal transistor that turns on and off to 12 volts on this side, so that the ground passes in and out. Okay, to go along with the idea here, again back to the block detector board, the center terminal here on the block detector board, that's the signal. So you would feed 12 volts into the block board. The signal wire would come directly to any one of these terminals here on the inputs. and then it would be detected by the chip and fed up to the computer. This is the baby brother of the 16 input card. This is an 8 input card, so it's just half the size, but you can see I still have to have all my AC inputs. I still have to have my communications connection. I still have to have the chip, and I still have to have the opto isolator cards. So it's the same thing. It's just a smaller version. Okay, let's see what size these are. 6 inches by 6 inches square for the 16 input card. And then I'm down to about 5.5 inches by 5 inches on the 8 input card. So it did downsize slightly. Next is the 8 output card. Again, it's got a lot of similar components to it. I kept it as standard as I could. Along the edge, you've got your 12-volt input, your 18-volt AC input, and your RS-485 communications connection. And again, all the regulator circuits and the nano chip. Over here, I used individual opto isolators to control the output transistors. I went with individual ones instead of the 4 in a case design because I found it easier to do the board layout. But they do exactly the same thing. The transistors allow up to 1 amp of constant current so that you can have a heavy draw device like a relay or something of that nature that needs a little more current than the 40 milliamps that the nano chip can put out. So along the side again, here's the termination for your 8 outputs. You would feed the ground out through the device and back in to this side, so that these transistors are acting as open collectors, which means they'll put 12 volts positive on these terminals. And again, I protect the card with blocking diodes, so if you reverse bias anything, the card doesn't get damaged. And this is 8 inches by a little over 5.25 inches. So it's reasonable in size. Then I have the combination card. Now this card has 8 inputs up along this end and 8 outputs down along this end with the common ground. Okay, so we've already discussed all the power side again and the communication side, so let's not drag into that too much. Again, I used single optocouplers because it was easier to lay out the board doing it that way. Here you see these optocouplers, there's 4 in each one. So these chips do the same thing as these, just they contain 4, this contains 1. Okay, so 8 inputs, 8 outputs, good combination board. Right, and that's 7 inches by 7.5 inches. This is my Tortoise matrix card. Okay, this is the card that caught my interest and got me started on this whole idea. And again, along this edge, you got your 12 volts, your 18 volts AC, all the regulator circuits for it, and your RS-485 communications, and the nano chip. Okay, and here's my opto oscillators that keeps the 12 volt circuit over here from interfacing with the 5 volt circuit on this side of the card. So the control lines come out And let me see if I can get this angled up so you can see it. There we go, there's a good view of it. And here you can see the copper trace running down through these little squares with the holes inside of them. I can't get that to focus any closer than that. Okay, but each one of these squares has got a hole inside of it. And then between each one of these rows, you can see the holes that don't have a copper trace. Okay, now if I turn this card over, and try to get a better view. Everything's backwards in my camera, so you can see me moving in the wrong direction. Here you can see the copper traces coming up and down on this side, okay, off to this terminal block on this side. So I've got one row of copper traces on the bottom from the terminal block. I've got one row of copper traces on the top coming from the computer and the terminal block on this side. Okay, so what you do is you put a diode between these two rows to select which tortoise motor gets connected to which route. So I've labeled them, and maybe you can read it there. It says route switches. Okay, the rows on the bottom connected to the route switches over here. Okay, the rows on the top connected back to the optocouplers and to the nano chip. Also, they're connected out to this terminal strip to the actual tortoise motors. This card supports 4 tortoise motors. So I have a driver chip. Actually, it's a 556 timer chip that I'm using it like a driver because they have 200 milliamps output, and I've designed the circuit here to make them act as a flip-flop. So these are the chips that are acting as your polarity switchers. Right, so they're reversing the terminals 1 and 8 out here on your tortoise motors. So the computer can come down through the wire trace and to the driver motor and select any of the 4 tortoise motors. And the tortoise motors are labeled A, B, C, and D in here. Okay, kind of visible underneath the wiring there. The routes are also labeled A, B, C, D, and E, but they're in lowercase to help distinguish them from the labeling for the tortoise motors, which are capital letters A, B, C, and D. So the options here, you can go from the computer, you can tell which tortoise to open and close or turn out, or you can command a route down through here, and you can control the 4 tortoise motors and a route. To go along with that, using the diodes, you jumper the control wire from the local route switches to the tortoises of that you desire on that route. And then from a local switch, you can throw a route. So you can use this card without a computer if you desire to, and still have routing. Next to it, over here, I also have switch terminals labeled Tortoise switches. So from the local fascia, you can put in a local switch and individually control each of the 4 tortoise motors. So the card is pretty flexible. You can control the 4 tortoise motors individually. You can control the 4 tortoise motors as routes locally, or you can control the tortoise motors individually from the computer, or you can control the routes from the computer. So that makes everything handy to control 4 tortoise motors either individually or as a route. Now there's a sister board that I've got mounted onto this little green card over here. I designed this card to help in establishing your routes. So what you do is temporarily you connect your 4 tortoise motors over here, A, B, C, and D. And then you can control your tortoises with your local switches, and you can set them to the desired route. When you do that, these LEDs, they're bicolored. Okay, they're either red or green depending on the polarity. And the polarity that we're interested in is the negative side. So we know which is our diode side. Okay, so I've labeled over here, green is negative, red is positive. So you locally just throw your switches, get your route set, and each one of these will have a red and a green, red and a green, red and a green, red and a green indication. So you remember the green ones. And so here, for example, here's tortoise motor D, terminals on the tortoise motor 1 and terminal 8. So let's say terminal 1 has got a green light on it. That means that terminal 8 has to have a red light on it. And the tortoise motor is thrown one direction or the other. So remember that D has a green on wire number 1. And with that information, we can come back over here to our matrix, and we would find the route for tortoise motor D. Okay, the controls, I should say, for tortoise motor D. Then we would select which route we want to put that on, A, B, C, D, or E. And we would put a diode from the control to the route, making sure that the negative side of the diode is to the route. I know that seems like a lot, but it's really simpler than it looks once you've done it. Okay, so that's the big brother of them all that I've designed, is this route card. Now, sometimes you just want to control the tortoise motors without routes and make life simpler. So I downsized the card. I took the matrix for the routing out of the card, and as you can see, it downsized the card quite a bit. Let's actually put it on top of the other one. Yeah, you can see that it really downsized the card a lot. So this is the identical card to the one we just talked about, except that it doesn't have the routing matrix involved. So again, I have power in on this side, and communications on this side, right? And I have the tortoise switches wired in here, and the tortoise motors wired over here. Again, A, B, C, D. Okay, so I'm controlling four tortoise motors, and they can either be controlled through the computer or through a fascia control switch. And by the way, they can be hooked up at the same time. Right? The computer can be hooked up at the same time that the local switches are on, and either one can throw it. That brings us to our last switch, or last card, I should say. Now, we've talked about this card. I actually did a clinic on this card, if you remember. This is the on-station card. Okay, it's 8 inches by 6.5 inches. And what this card does, okay, of course, it's got the standard power terminals over here and communications terminals, right? And whoops, this card doesn't have a nano installed on it at the moment, but then the nano chip goes here and controls the logic. And these are the opto couplers that separate the 5-volt circuit from the 12 volt circuit. Now this time there's 11 outputs and 3 inputs. Okay. Whoops, I gotta put another terminal strip on that card, guys. Thanks. I didn't catch that. I missed it. Okay. So there's 11 outputs here, 3 of which are missing. But I gotta put them in. And then there's 3 inputs on this card. Okay. These outputs are meant to go to your signals on like the entrance of a passing sighting, and this would provide enough outputs for full signal control of that output of that sighting. The inputs give you the feedback that tells you either the switch is closed or thrown, and the switch is, since it's an on station, it has block detection for it, so that the dispatcher knows that there's an actual train in that block and that he can't throw that switch. Okay, so since I've covered this so much in the clinic, I'm not going to go into much more detail about it. I just wanted to show the group what I've been doing and what I've done. So I have 5 of these cards. I have 5 of the Tortoise matrix cards. I have 5 of the mini Tortoise cards. Actually, I just got 5 of everything, right? So, except for the block detectors, they've got I've got 20 of those, so I can control a pretty good sized layout here. One more thing I wanted to point out that I haven't done yet. Let me bring back my 8 input card again. One thing that I didn't discuss on this was the fact that it's not only 8 inputs, but it's an output card too. But it's not a digital output card. It's an I2C output. Okay, an I2C is a communications protocol coming out of the Arduino chip, out of the Nano. We communicate through this to other external devices. And what I do with that is I use a pulse width modulator card. Now, I didn't build this card. I simply purchased this card. It was so cheap. I think it was like $3-4 to buy. I got about a half a dozen of these. No, I got a dozen of these coming in the mail on a slow boat from China. Okay, you know how that goes. So this pulse width modulator card connects, these 4 wires connect right here to the I2C communications protocol. Okay, and this card requires 5 volts to drive the external devices that I've got wired here. So what I do is, again, I bought this little voltage regulator card, and these were $2, $2.50 each. So I couldn't build them that cheap, so I just bought them. Okay, so on the input side, I feed in my 12 volts, you know, so I don't have to have a special power supply under the layout. So I just feed it in 12 volts, and I want 5 volts out. So I adjust this little pot until I get 5 volts on the output wires. And that then feeds my 5 volt input terminal here, okay, for my pulse width modulator card. And that drives my servos. Okay. Now, another thing you can do with this little card, just as a side note, since I can adjust the voltage, you can use that 12 volts coming in and hide this inside one of your buildings and adjust this down to 3 volts and then drive your LEDs off this little card. That simplifies life, and again eliminates the need for a specialty power supply under the layout. You can use your standard 12 volt power supply. So let's talk a little bit about this pulse width modulator card, okay, and how I use it. You can see all these wires hanging off of it. And here's a pile of servo motors, little individual servo modulators. Let me pick one up here with an arm on it. And what I do is in the Arduino chip, I tell it that it's looking at an output, okay? In JMRI, I configure JMRI to control a turnout. And I tell it you're controlling a turnout with only one output. So that means when it's on, you've thrown the turnout. When it's off, you've closed the turnout. Okay, as far as JMRI logic is concerned. So when that bit comes in to the Arduino, I have code in there that reads that and says, okay, convert that and send out on IC squared over these 4 wires, right? Send out on IC squared the command to control servo 1 through 16. And then I also send with it what I want it to do, how many pulses in which direction I want the servo to move, and I control that servo. And I've made a simple replacement for a tortoise motor. And I bought a dozen of these for 20 bucks, I think it was, less than 20 bucks. Okay, so you can see that I'm getting cheap. So that's an advantage over the tortoise motor. The disadvantage is that I have no feedback with this. If I want feedback for this turnout, then I have to put an external circuit on it to control that. But all in all, it's a good combination. It's cheap. So I have 8 outputs on that input card as well. And I thought I'd better mention that to you. As I was saying, that kind of wrapped things up. So if you got more interest and you want to know more about it, you can go to Github. Again, it's listed down below. Have fun with all this. I hope to share it with you. Thank you.